should be on Wednesday's assignments page, not on Thursday's assignment page. And you'll have to correct me because when I click on certain things, it goes back to today's. So just, if it doesn't make sense, help me out, okay? It would if you saw what I did with last class period. So we'll just say that. All right. So yesterday, before I was so rudely taken out of class, we were looking at interaction. I had recorded a video with fourth period. And for whatever reason, it was very slow to load. I don't know why. I'm sorry. I don't get to control YouTube or our technology here in the district. So there are some vocab that we're going to work on. So you do need to open Canvas. If you don't already have it open, go ahead and do that now. Okay, and what we're looking at, now that we can make graphics appear and make them move, we're going to explore controlling those images on screen through input, specifically through the mouse and the keyboard. Okay, now, remember that the definition of input is simply how the user communicates with the computer. So far, everything we've done has been text-based using the console, but there's other ways to provide input. It can be with the keys on the keyboard, it can be with your mouse, it can be with a joystick, a touch screen, a camera, a scanner, a game controller, all of those things. So, we didn't even get to play hot or cold yesterday then? No, we didn't. All right, so I'm going to send Adnan is going to make a quick jog in one cafeteria door and out the other and then come back. Okay?
She said jog. Jog, fool.
Okay, I have this. I'm going to hang on to it. You guys need to pretend like you're holding on to something in your hand. Everybody needs to be holding on to something in their hand. Okay? No. Pretending that you are. Okay? I hear him. All right. We're playing hot or cold. Okay, hold on, don't sit. You have to go and find the object that somebody is holding in the room. You can go tap on them, you can ask them, but you have to move. You can't stand in one place. You are cold. You are colder. You are freezing. You are living with the penguins in Antarctica. Do you know the game Hot or Cold? Adnan, do you know the game Hot or Cold? Well, did you hear me tell you that you're swimming with the penguins in Antarctica? That's how cold you are. You're not quite as cold. You're still cold though. Yeah, you're getting colder again. You are warming up a little bit. A little bit. Okay, have a seat. All right, so playing this game, obviously most of the other classes, anyway, when they were guessing, the clues as to being cold or warm or whatever helped them find the object, the hidden object, within, I don't know, a few guesses. Let's say that I didn't give you any, I just made you guess and you didn't get any feedback. Would that make it easier or harder? Harder. Okay. So, that brings us to how many people did you ask? Like
I never counted.
Five or six, something like that? Because you went backwards a couple of times too, which,
Yeah.
all right. So, and then how did you decide what to guess next? Like once you guessed once, how did you decide to guess the next time? Like what made you choose to go a certain direction rather than another?
I just wanted to go this way.
The right answer would be based on the feedback of being hot or cold. Okay. All right. So that brings us to interaction. Interaction is a cycle of user input and program output that influence each other. This should be in your vocab. A cycle of user input and program output that influence each other. Somebody has stolen my little Nerf football, otherwise it would be flinging across the room at your head at this point. Okay, so most programs are interactive in some way. Even most of our simple console-based programs have been interactive because the user's input influences the outcome. The main difference is now we're going to learn about other more common types of input. So let's open part 2, Frog Race. And there are a few things that I want you to try to do. And they would be to, if you look at it and make it run, you are going to see that you have a P. And if you hold the P down, it's going to stay in the air longer. The other key is the Z, and it doesn't matter how long you have it in the air or have the key pressed, it takes the same leap. Now, I do see that if you press it really, really fast, then it doesn't have a chance to go back down, but you are racing the frogs using P and Z. Oops. Okay? And then you have these 3 things which you are looking to change. I'll give you 2 minutes to look at it. You want to change which keys control the frogs. You want to change how fast the frog moves while in the air. How fast the fast frog moves while in the air. And change how long the slow frog's jumps last. Okay, so if you look at the code on lines 35 through 44, nope, actually starting at 35, you're going to see the slow frog movement. If TSAP was key pressed, and it says TSAP dot capital K underscore Z. So we'll get to that in a minute, but that Z is indicating that you are using the Z key. So it could be any key on your keyboard. If it's a letter, just use the lowercase letter. If it's a number, use the number. However, if it's the space bar you want to use, you would type space in all caps. If it is the arrow keys, you would write left, right, down, maybe up in all caps. If it's the return or enter key you want to use, you would write enter in all caps. Now, one of the requirements was to change how long the slow frog's jump lasts. So if we look at the X speed, the X speed is 50. Well, what happens if we change that to 250? He takes bigger, longer jumps. Yes, Tony, stop. So annoying. Okay, so that was 37, the X frog slow dot X speed. I increased it to make him jump farther. Now, it started at 50. I could make him jump smaller, too, but then he'd probably get nowhere. So the other one we needed to do was change how fast the fast frog moves while in the air. So I can go down to 47, and I can see that frog fast dot X speed is currently at 100. Well, what if I up it to 1,000? Well, you have to hold it down because it's while it's pressed. The frog, the fast frog, I changed its Y speed or X speed from 100 to 1,000, which might be a little much. So I may make it 500. But basically, while your key is down, oops, wrong key, it jumps. Okay? All right, now let's go to the next one. So our vocab we want to add is called an event. Those of you that did principles, you will remember event handlers. And it's basically a single action that occurs as a result of the user. So an event can be something that you do. You can press a key. You can hold down a key. You can release a key. You can do the same thing with your mouse. Those are events. So, a few important things to remember about events. An event is one specific action, and events happen instantly. So an event is when the computer informs the program that the user has taken some action. This can be things like clicking the mouse button or closing the program. Because they are performed by the user, the program can't easily predict if and when they are going to happen, so we have to manually check for them. The syntax here asks the question, did the user click down on the mouse sometime during the last frame? Because remember, these are animations you're doing, right? So that's where the last frame comes in. It's not, was it mouse pressed ever? It's, was it pressed in the last frame? So if you visualize here, pressing down on a key or on a button of any kind, that's your button press. You also have the ability to have a while down, which you'll see in a minute, but when you release it and the button goes up, that is the button release. So those right there, what you see are two different events. The moment the button is first pressed, the moment the button is released. There are some actions like clicking and dragging where something different happens when the button is pressed versus when it is released. And that's why we have to have both of those events. So let's look in our project panel at part 3, paint thrower. So currently, nothing happens. We have a stage with an easel on it. If you look at the in assignment panel, you're going to see you have 3 functions in the library: make paint, splat paint, and erase easel. So if we look down in our code, we have 2 parts that are open for us: the blob creation and the easel erase. So these are in the main loop. So under blob creation, we're going to put an if statement saying if tsapp dot was mouse pressed, then we are going to do the function tspaint make paint window. Okay, so go ahead and add that. And then when you're done, check it. It is checking to see if you press on your mouse key, your mouse button. Each time you press on your mouse button, it throws paint at the easel. So every frame when the main loop repeats, we check to see if the mouse was clicked the last frame. If the answer is yes, we throw paint. This checks for the mouse being pressed down. Obviously, we just learned there's another matching function called was mouse released that checks if we release the button. So if we wanted to do something like this, but with a keyboard key, we would need an additional piece of information. The function would need to know which key we were checking on the keyboard. Okay, does everybody have this piece of code in now working? All right. So if we need a key on the keyboard, we have to use what is called a key constant. So a key constant is an unchanging value representing a key on the keyboard. So we've had a constant before when we used colors using in the TS app. So instead of knowing the data that represents them, we just used a constant to name those colors. Well, we're going to do the same thing here with the keys. So key constants are useful for a similar reason. Normally, each key on the keyboard has a number that the code uses to identify it. However, because it would be very hard to memorize over 100 numbers, we make it easier by giving them names. So a key constant always starts with tsapp.K_, and then you give the lowercase letter or number that you want to use. Again, there are other common keys that you can use that you can find in the code assist. But if you wanted to do space bar, left arrow, right arrow, down arrow, or the return or enter key, you type those in all caps. Then we have state. And a state is information that is remembered by the program. So in this one, it is asking if mouse is down. What do you think is mouse down? We know is mouse pressed, is mouse released. What is mouse down? Holding it. Yes. I need that foam ball. Where is that foam ball? I found it. It's not the football. I don't know where my football is, but I found something to throw. Oh man, and now I lost it. All right. So, unlike an event, which happens suddenly, a state is some piece of always existing information. Okay? So, we can check what is the state of the sky, and you could answer The sky is blue, the sky is gray, the sky is dark, the sky is bright, the sky is cloudy, whatever. So there is always known information about something. And the program is storing it. And we can check in on it occasionally if we need to know it. So the syntax presented here asks the question, what is the current state of the mouse button? Is it being held down? Since a button only has two states, down or not down, this can be a Boolean because it can be a yes or a no. So just like for the events, there is a version of this for both the mouse and the keyboard, but the keyboard version needs a key constant. So, because states, unlike events, are just information, they can be true over a period of time. This is the main difference between when you should use events and when you should check the state. Events are for did something happen, and states are for does something continue to be true. And what you might want to include here with this for your events and your state, an easy way to remember it is events are for code that needs to run when something happens. States are for code that needs to run while something is true. Remember that. Okay? So events are for when. Events are for when. States are for while. Any button press on mouse or keyboard is made up of two events and a down state that continues for a period of time. As you can see here, when you hit the keyboard, there is an instant event when the key is pressed. Then there is some period of time during which the down state of the key is true. Then there is another instant event when the key is released, and the key state goes back to being false. Let's go to part 4, frog jump. And what we want to do is we want to power up this frog. Okay, so right now, I forget, it's with the space bar. When we hit the space bar, it looks like it's reaching up. Okay, and then whatever. So what we want to do is power up this little frog so that we're holding down the power key so that the power keeps increasing for every frame the key is held down. You'll see the power up in the top right corner. You'll see that it stays at 0. So under the power increase comment, which is down on line 32, we are going to add a conditional, an if statement. If tsapp.was key pressed, and we're looking at a key constant, which is the space key, then we're incrementing the frog power by 1. Once you get that in, run the program, see what happens, see what changes you made. Yes.
Why is there
Why is who,
who looking two different conditional,
what?
why are we making two different if statements with the same conditional? Lines 32 and 37 have the same condition.
Because one of them is, well, if you look here, this one is incrementing. This one is changing some different things. Now, technically, maybe we could have just, and we'll try this and see, we could have just added this there. Maybe. Don't do anything yet. Okay, yeah. But I don't know, there might be something, because we're going to be adding to it. So I don't know if there's some more stuff that would throw a kink in that. But we'll look and see. So right now it looks like you should be able to add that. All right. So what do you notice about how this code works? Every time you press the space bar, he still reaches. You can see the number increasing to 1. But then when you release it, it goes back to 0. And that's because it only runs when the key press event happens. We can only get 1 power no matter how long we hold the key because the event only happens once. So we probably want to replace this with something that just checks the current state of the key. So we are going to change this from was key pressed to is key down. And now that's why. Is key down. And now check it. So while you're holding the space bar, it's increasing the power. And then when you release it, the frog flies into the air. Okay? Yeah, so 32 changed from was key pressed to is key down. All right. Now we have duration. And duration is the amount of time between 2 moments. So there is an actual function in the TS app called get program duration. And what it does is it measures 2 things. From a specific point in time to where it is now. So sometimes we want to know how long it is between 2 events or how long it has been since a state changed. To do this, we need to calculate duration. So this syntax returns the amount of time that has passed between the window being created and now and where it is right now. So where that code runs right now is what it's looking at. And it measures it in milliseconds, which is 1/1000th of a second, meaning 1,000 milliseconds equals a second. Here we have then, now, and in between is the duration. So if you were telling time on a clock and you wanted to know how long you'd been sitting in class, you'd look at the time now, you'd subtract the time that you got in, and you would get the duration. Let's go ahead and go back to that part 4 high jump. We're going to add a little bit to it. Let's say we only want the frog to leap up for 2 seconds before falling back down. We could measure the frog jump's duration, but we would need to know when the frog last jumped so we can test the duration of the jump. So we're going to find the jump section, which already has code in it, and we are going to add 1 line of code at the bottom. Make sure you indent it. We are going to do frog jump time equals tsapp.get program duration. Go ahead and get that one in there. Okay? And then when you run it, it's not doing anything that you see at this point in time. It's just measuring the amount of time. So now that we know when the frog jumped, we can test how long it has been. We'll also want to make sure the frog can't start falling unless it is currently jumping. So it doesn't just fall down if we let it sit there. So there is an entire fall section, and there is a few lines of code. We are going to say if frog.yspeed is less than 0, then we are going to have a nested if statement. If tsapp.getProgramDuration minus frog jump time is greater than 2000, then frog yspeed equals negative frog yspeed, and frog image equals frog4.png. Okay, so let's get that in. Okay? Now, if you run it, what happens? It's going to come back down. Okay, did everybody get that working? All right. Let's look at the next slide. Okay, so here is some code right here. Let's look at it. So it starts off, it's saying last. Last equals 0. And then while window is running, you have a variable called now that is getting the duration from that function. And it says if the mouse is pressed, then time since equals now minus last. And then last takes the value of now, and then print time since divided by 1,000. What do you think this does? You're getting there. So first off, notice that the print statement at the end. It's printing the duration between two mouse press events by subtracting the time of the last mouse press from the current time of the mouse press. Of when they happened. Of when they happened. Yeah. So last equals now. We are saving time from the last time the mouse was clicked so we can use it in our next calculation when we have to look, when it runs through it again and it's looking for the next time. And then, of course, it's dividing it by 1,000 because then it's going to give it to us in seconds as opposed to in milliseconds. If we don't assign last a value, we're going to get an error. So we're assigning it 0 in this instance. At some other time, we may give it a different number, but right now we give it 0. And usually you do have to assign a value to a variable before you run it through a loop. Okay. All right, so some things to think about here. We are next going to test whether sprites have run into each other, whether they have been clicked, and get information about the mouse pointer. Okay, so let's go to yesterday's Meadow Madness. Let's look at yesterday's Meadow Madness. All right. So when we look at this, we can run the solution. And you can see that a flower will bloom in the meadow. They're growing out of control, so we have to fix the program so that they appear every 2 seconds instead of every frame. So right now, this is what it looks like. We only want it every 2 seconds. So right now, we have the window created, we have the background, we have the main loop while window is running. So we do need to do one thing. Before that, while window is running, we need to get a variable called last flower, and we need to get the value based on tsapp.getProgramDuration. That is on line 26. Now, under flower generation, we have some pieces given to us, but it's incomplete. So we actually need to have another variable. We need to have now, and it is also going to get its value from tsapp get program duration. And then we are going to say if now minus last flower is greater than or equal to 2,000, that's 2 seconds, then we are going to do some things, and I am indenting all of those things there. And I'm going to add one more thing, which is going to be last flower equals get program duration. So we were getting program duration 3 different times. We added it up here with the getting it for the last flower. We then did it right here under flower generation. We added an if statement measuring or comparing, not measuring, well, we are measuring, if now minus last flower is greater than 2,000, it is then going to change the x coordinate, the y coordinate. The flower is going to, it has the sprite, it has the scale, it's going to add it, and then it asks one more time for this last flower. And why do you think that is doing that right here at the end? It's doing it again because it's going to go through the while loop, and this one is not in the while loop. So it needs to check it at the end. Excuse me. No. All right, let's go ahead and once you get that in, let's go ahead and go to the next one, which is night flight teach. So in this one, this flight animation is missing interactivity. You're going to rotate Abby while the mouse is held down and increase her upward speed when the mouse is released. Decrease Abby's angle by 5 while the mouse button is held down. Increase Abby's upward speed by 75 when the mouse is released. You're going to use is mouse down and was mouse released. Your solution looks like this. And notice that when you click on the mouse, Abby's rotation changes, allowing her to fly. And then this one, all she does is fly forward, and that's what we need to fix. Okay. Here we got background. We've got her speed set at 0 for Y and 100 for X. We have our while loop. And it is asking if while window is running, if Abby center X greater than or equal to 850 or less than 150, okay, then Abby flip X equals not Abby flip X, Abby dot X speed equals negative Abby dot X speed. If Abby center Y equals 400 or greater than or less than, or sorry, greater than 400 or less than 100, then Y speed equals negative Y speed. So we need to look at spin, and we need to ask if TS app dot is mouse down, because we're checking to see if the mouse is being held down. Remember, that is a state rather than an event. Then we change Abby.angle, incrementing it minus equals 5. Then we look at the speed change, and we are going to say if TSApp dot was mouse released, Abby dot Y speed minus equals 75. So we're looking at those two things. When when you get it, test it, see if it works. Make sure you are submitting all of the pieces for Wednesday's class, and then we're going to move to Thursdays. As soon as you test it and get this in, yes, we are. The video not working yesterday put us a little bit behind, so I'm flying us through. Okay, so we're going to skip today's warm-up because we've gotten warmed up. I'm going to unlock the instruction. Okay? All right. So we are now looking at collision. You are still adding to your Canvas library. Okay, so hit submit for me, unless you, for some reason, need to go back and fix something at a later time. So we learned about how to use how the program can interact with the keyboard and mouse. Now we have to learn how sprites can interact with each other, with other sprites, as well as with the mouse. So let's say we have a car sprite like this in a program. If I wanted to test if a specific point on the screen is touching this car or not, I would need to keep track of where all the pixels of the car are and then see if the point is in one of those pixels. Well, that would be the very professional way to do it. However, it's also a very time-consuming way to individually check all the pixels. Mathematically, it's much easier to test the point if it's within a certain area. So the fastest shape to test mathematically is a box. It's very easy to tell if a point is in a rectangle area, although sometimes a circle area can be used. So in a professional setting, it's common to create something called collision boxes. These are a combination of rectangles that together define the shape of a sprite. Again, we can simplify it even more if we use just one single rectangle. Doing lots of little ones requires special tools to create the complex sets. So we want to look at Hedgehog Launch. It's part 2. If we look at it, the hedgehog is running kind of across the screen. If we click on the apple, it gets big. And when the hedgehog touches it, it moves to a different place. Okay? So what I want you guys to do is see if you can make the hedgehog, go through this one thing, see if you can make the hedgehog stop further from the mouse pointer and change how much bigger the apple gets when you click it. Okay? if you can make the hedgehog stop further from the mouse pointer, and then change how much bigger the apple gets when you click it. See if you can find that in the code. All right, so I am writing a note that tomorrow we pick up on slide 5, which means we're going to be buzzing through tomorrow's assignment as well to try to get us caught up.